Hi, my name is Matt Scare, and I'm a Principal Data Warehouse Specialist Solution Architect here at AWS. I work with people both new to AWS and existing customers interested in data warehousing, particularly with the Redshift service. In this role, I see a variety of use cases. Some customers are young tech companies that are employing a data warehouse for the first time. Others are Fortune 500 companies who are opening up their data to a larger population of analysts to generate new insights. As you might imagine, the scaling needs are hugely different across this spectrum. For instance, young companies may not have years worth of baseline to know exactly how much capacity to deploy at any given point. So they're looking for a fair bit of elasticity in their data warehouse so they can react to demand quickly and scale up when demand increases and scale back down when the demand subsides to save cost. And they want to do this with the minimal disruption to their analysts. At the other end of the spectrum are big companies who want to ensure that their reports run blazingly fast, even if thousands of analysts start querying the data at a given instant. And they want to do it in a way that doesn't put a burden onto data engineers to be constantly monitoring demand and adjusting resources. Or the companies may even want to automate some of the repetitive tasks so the data engineers can focus on more interesting or value-adding work. A common question I get asked by all these organizations is that with the new paradigm of constantly scaling up and down, how can they ensure that their clusters are optimized? Will they need to constantly defragment tables? Will they need to be constantly updating metadata? Data engineers across the spectrum want to move away from these day-to-day admin tasks so they can focus on value creation activities for their organization. Fortunately, with Redshift, they can do just that. So today's session shows how Redshift addresses all of these needs, helps you scale storage and compute resources on demand and even automatically, and maintains cluster health with automated administration. Just to set the stage, some of today's content is a refresh from reInvent 2018, and some of this is new information. So here are some of the takeaways from today's session. How to scale compute and storage quickly on demand. Here we're going to compare and contrast Elastic and Classic Resize. I'm already seeing wide adoption of Classic Resize across the spectrum of customers I talk to. Next, we're going to look at how to scale compute automatically to handle thousands of concurrent users and queries. Customers on the preview for this service are sharing their independent testing results with us, and it's looking very encouraging for this to become a go-to resource for systems with chunky throughput requirements. And then finally, we'll understand more about Redshift intelligent administration and maintenance. I was just on site with a large financial institution on the East Coast, and they're reducing the time they allocate on the weekend to perform their vacuum of statistics gathering. This is directly attributable to the automated vacuum and automated analyze functionality we've added. Let's start with reviewing the Classic Resize. In this, it's fairly straightforward. So you choose two things. You pick the new node type and the number of nodes and press go. Behind the scenes and on your behalf, Redshift is taking the following actions. It's taking a snapshot, which is an incremental snapshot of the current cluster. It's provisioning an entirely new cluster and hydrating that entirely new cluster from the snapshot data. And then as a final step, Redshift will switch the endpoint to point to the new cluster. A little bit of fine print on the Classic Resize. During the operation, the cluster is in a read-only mode. Next, the size of the resize is available via the console and also via API calls. The resize operation can be canceled up to the point of the endpoint switch. So almost for the entirety of the resize operation, you can bail out if you want to. And of note is that table statistics are gathered automatically as part of the resize. Similarly, a vacuum delete is achieved automatically, and this is done by Redshift not moving the blocks that have been marked for deletion. The sort order of the rows is maintained, however, so the data is no more and no less sorted than before the resize took place. System tables, such as STL query, are reset, so no history will be maintained across the resize. The resize operation is the runtime of the resize operation is a function of the amount of data to be restored. In large clusters, it can take several hours. Redshift will move blocks first that are being requested from the read-only queries being executed against the cluster itself. This performance optimization makes a large difference in the perception of the classic resize operation. We'll discuss the analyze and vacuum delete operations a bit more in the latter half of the webinar. So now let's compare that with the Elastic Resize. Elastic Resize is a new feature which enables scaling of Redshift up or down in just minutes. When a customer enables a classic resize, Redshift adds additional nodes to the main cluster and distributes data across the new configuration in minutes. This new feature is a significant improvement over the classic resize offered by Redshift, in which Redshift historically would have provisioned an entirely new cluster. This Elastic Resize will change the number of nodes in the cluster. When you go from 3 to 6 nodes, previously we would have had to redistribute all the data. With an Elastic Resize, we can bring in the 3 extra nodes that customers requested automatically. The resize operation takes around 2 to 5 minutes and then becomes available. With Elastic Resize, customers can increase the size of your cluster's compute and storage easily and quickly to process complex workloads and decrease query response time as needed. Many Redshift customers have workloads which need additional and storage resources to meet their growing requirements or to meet a demanding workload. For example, an ETL workload for certain hours in a day or even month-end reporting may need additional Redshift resources. Elastic Resize will make Redshift significantly faster, and customers can pick the resize option on their console or schedule the resize and let Redshift handle the rest. So let's review the specific steps that Elastic Resize is taking. So whereas in the classic resize where you were picking the node type and count, with the Elastic Resize, you just pick the new node count. On your behalf, Redshift will take the following actions. It'll again take an incremental snapshot of the current cluster. Then connections will be momentarily held while the metadata about the database is copied to the new nodes. This is typically a very small amount of time. In the case where we're increasing the number of nodes, we'll provision those new nodes, and then those new nodes, the new cluster will be hydrated from the snapshot. This is done at the slice level. A bit more fine print on the resize. So in contrast with the classic resize, in the Elastic Resize scenario, the cluster is available for both reads and writes during the resize, except for that small moment when the metadata copy is happening and the connections are being held. The status of the resize is available via the console or via API calls. In the case of an Elastic Resize, there's no automatic vacuum nor analyze associated with the resize. However, the system tables are preserved across the action. We see that the resize operation runtime is on the order of a few minutes. And before the resize will start, Redshift will automatically validate that there's enough room for the scenario where you're reducing the number of compute nodes. Redshift itself will move the blocks first that have been requested from the queries that are being executed. This is an important performance optimization. For smaller node types, you can either double or halve the number of nodes. This is for the dense compute 2 large and the dense storage XL. For the larger node types, you have a bit more flexibility. You can resize anywhere up to double the number of nodes or down to half the number of nodes. This is for the dense compute 2, 8XL, and the dense storage 2, 8XL. We'll look at the graphical representation of your resize options in the next slide. Here's a visual display of the Elastic Resize options based on the node type. Note that in the DS2 8XL and the DC2 8XL scenario, there are fine-grained options available. For example, if you had a 10-node cluster, you could elastically size up to 20 nodes, even going from 10 then to 11, 11 to 12, and on and so on. We expect that most resizes will be Elastic Resizes. Here's a simple decision tree to summarize the exceptions to the just elastically resize it rule. And then here are a couple of example use cases. The canonical example would be month or quarter end processing. This exact scenario came up on a call this morning with a utility company I'm working with. Here are a few frequently asked questions about Elastic Resize and Classic Resize for that matter. So the first one is when to pick an Elastic versus a Classic Resize. A few points to this. Across the fleet, we expect to see most of the resize activity to be an Elastic resize. Of course, if you're changing the node types, Classic is the option you'd want to pick. Similarly, if the desired new node count would result in an imbalanced system with respect to slices, Classic is again a good choice. Redshift enforces this automatically before you initiate the resize. Successive Elastic resizes in the same direction that would cross the 1/2 or the 2x boundary are not allowed at this time. Another question that we commonly see are, what are the factors to estimate the resize runtime? So in the Elastic resize scenario, we expect the cluster to be fully available for reads and writes in a single-digit number of minutes. It's also interesting to note that there's a bias towards moving data that's needed by the users. And we see in practice across the fleet that about 20% of the database blocks meet the needs of 80% of the workload. So the data movement will continue in the background hydrating from S3. Another question we see is, how can customers test the Elastic resize offline? So customers, of course, will want to experiment with this new functionality. An easy way to do this is to take a manual snapshot and try restoring it, and then remove the cluster when you're done. And then finally, or next, how do we track the progress of an Elastic resize? Both the Elastic and Classic resize are tracked on the Redshift console, and CloudWatch metrics are generated during the course of the resize. And then sort of in summary, what are the current constraints on Elastic resize? As mentioned earlier, there are a few guardrails. The node type doesn't change. So if you want to change your node type, the Classic resize is the option. And then in the decreasing compute node scenario, Redshift has to be confident that the data will fit. It'll check this automatically before the resize is started. And then in order to maintain a balanced system with respect to slice count, Redshift will guide on what's a legal move. This is the 1/2 to the 2x constraint. It's good to note that with the larger node types, this becomes increasingly flexible. As with everything with Redshift and AWS in general, it's great to stay tuned as we continue to evolve this service per customer usage. Now we'll switch to how you can dramatically increase both the concurrency and the throughput of the cluster in a completely transparent fashion to your users. Notably, this flexibility to choose how to scale concurrency is at the workload management queue grain. This is a key differentiator from other services. So workload management, again, is you may hear that as WLM. Let's add a little bit more detail on how concurrency scaling can help with the different workload queues we just talked about. For instance, you may have a major ETL workload running to onboard new data sources, and you wouldn't want mission-critical ETL workloads to be adversely affected. With concurrency scaling enabled, Redshift will automatically deploy additional resources so that all of the workloads run without any queuing at all. Similarly, if your cluster gets a sudden spike from hundreds of analysts concurrently running queries, concurrency scaling will ensure that their workloads get consistently fast performance, just as if they were the only one querying the cluster. So let's dig into concurrency scaling a bit more. Concurrency scaling is planned to be released to general availability very soon. We're in the process of completing an extensive preview program with several customers across the usage spectrum. At the workload management queue grain configured by the customer, concurrency scaling can spin up additional Redshift clusters when queuing is detected in a WLM queue on the main cluster. Users connect to the main cluster and Redshift routes queries in a completely transparent fashion. When the queue has been eliminated, the new transient clusters are automatically released. There's no hydration period for the new clusters. They are reading directly from the Redshift snapshots and are complementing that with data from the main cluster. ACID is maintained, and it's not possible for queries to execute on stale data. For each day in the month when the main cluster is up, the cluster accrues an hour of free concurrency scaling. From our fleet-wide data, we believe that this free concurrency scaling will cover the use case for greater than 97% of Redshift's customers. Any use in excess of what's free will be billed at 1-second intervals at the cluster's current rate. A bit more fine print on concurrency scaling. Again, this is controlled at the WLM queue level. So you may want to have a WLM queue for which you don't want to spin up a new transient cluster, say an intern queue workload or something like that. So you could set that to never scale. On the other hand, you may have something like a reporting queue where concurrency scaling could really help. This workload management queue could be set to auto, and additional clusters will be spun up if queuing is detected on that queue. Redshift will automatically determine which SQL statements can be sent to the new clusters. For example, at the time of launch, DDL statements will remain on the main cluster automatically. This is once again handled completely automatically by Redshift itself. Again, at the workload management queue grain, you can specify the maximum number of additional clusters to be activated per queue. We'll continue to study and refine this process over time. Let's watch a couple of illustrations of this in action. Here's the pre-concurrency scaling world with the default queue and short query acceleration enabled. While SQA, or short query acceleration, is not related to concurrency scaling per se, I want to make sure I briefly talk about it here. Redshift uses machine learning to predict the execution times of queries ahead of time. It is then able to automatically route short queries to a dedicated queue so that they're not starved behind long-running queries. This is called SQA. With concurrency scaling, Redshift does something similar. It's again using machine learning to predict when queuing may start to happen. It deploys additional resources if queuing is detected or predicted. When the resources are deployed and additional queues are created, Redshift continues to perform SQA. The combination of these actions eliminates starvation in queuing, resulting in consistently fast performance, no matter the shape of your workload. Now we've enabled concurrency scaling against the default queue. Here you can see, as there are no slots available in the default queue, a transient cluster was spun up, and then once its allotment of slots filled up, yet another transient cluster was spun up. As the peak of that workload has gone past, the transient clusters age off and are automatically reclaimed by the system. So here's a more realistic example. In this case, we have a reporting in an ETL queue, and again with short query acceleration enabled. We haven't set either queue to use concurrency scaling, so you can see queuing occurring. And here we enable concurrency scaling for the reporting queue, but not the ETL queue. So we're going to allow the reporting queue to burst and create transient clusters, but not the ETL queue. And meanwhile, short query acceleration is continuing to do its job and pick off the very short running queries and running those on its own. So here are some frequently asked questions around concurrency scaling. Are there any constraints around what type of workload can be run on the new clusters, and does the customer need to control this? At launch, only read-only SQL can be assigned to the new clusters, so DDL and DML statements will need to execute in the main cluster. This routing is performed automatically. And then how does the customer configure concurrency scaling, and what are the options? So concurrency scaling is configured at the workload management, or WLM, queue level. Customers may elect to allow jobs against the dashboard to generate new clusters, but as our example showed earlier, not allow the intern queue to do so. These options are straightforward. It's either don't scale or automatically scale. And then finally, will I see a big cost impact during periods when concurrency or transient clusters are deployed? The answer is that most of the customers should not see any cost variation from their month-to-month bill. For every 24 hours that your main cluster is in use, you accrue a 1-hour credit for concurrency scaling. That means that concurrency scaling is free for more than 97% of the customers based on our current usage patterns across the fleet. This is a noteworthy advantage for Redshift customers to take advantage of over those in use with other data warehouse vendors, where elasticity often comes at the price of wildly varying month-to-month costs and creates budget runs for IT. With Redshift, that's not the case. One of my customers is a nationwide banking institution participating in the preview of this feature. They're seeing dramatic throughput increases when using concurrency scaling and expect to use it in production. Now let's look at the intelligent administration and maintenance update. Redshift is intended to stay as easy as you want it to be. If there are areas where you choose to administer something yourself, you'll have that option. Looking into the advances in administration and maintenance, it's great to see that more and more automatic options are there as well. Here are some of our key ease of use goals for the first half of the year. We'll look at this slide from the bottom up. The first two, automated analyze and automated vacuum, are in general availability already. That's the GA on the slide there. Auto analyze leverages a new Redshift worker construct and is set to start collecting statistics during periods of decreased cluster usage. Should user activity increase, the worker can pause their actions so there's no impact on the Redshift user experience. Similarly, Redshift workers can be programmed to automatically vacuum tables and step back if user activity increases. The next one is in preview with a selection of customers at this point. This is an automatic concurrency setting, and this is about creating a new option for workload management, as we've been talking about earlier, where we're having Redshift decide and monitor what are the most efficient workload management settings that can be put into place. The next is our on target for the first half of 2019. These are sort key recommendations, which are the next logical step in the alerts from the STL alert event log table. And we'll now propose a sort key based on the automated analysis of table usage. We'll do the same thing with the automated distribution key recommendations. Redshift will analyze the table attributes and the join characteristics to recommend an optimal distribution key. We'll start with vacuum delete. Automated analyze and vacuum delete have been live for a few weeks now. Across the fleet, we're seeing millions of tables being analyzed that had never been before. This helps to generate better execution plans. The automated vacuum delete itself reclaims space in the specified table or database. This has historically been a manual operation, and some customers didn't want to manually reclaim table spaces when rows were deleted. Now Redshift watches for relatively quiet times in the cluster and will pause itself if additional workload arrives to the cluster. Vacuum itself has been improved to enable this. Historically, vacuum was performed at the table level. This has been extended to the database slice level, which is a much finer grain. We also plan to extend this to vacuum sort, and the selection heuristic for which tables are vacuumed considers how frequently the table is used and how important the table is in need of being vacuumed. So now we'll look at auto analyze. Amazon Redshift now automatically updates table statistics on your cluster via the new auto analyze feature. Up-to-date stats help the query planner to choose optimal plans, and as a result, queries should run faster. With auto analyze, if the table data has changed, the statistics are refreshed for that table in the background. To minimize the impact on your workload, auto analyze yields to user workload. So now we'll look at some frequently asked questions associated with these two new features. 1, do I still need to run vacuum? At this time, vacuum sort is still needed to maintain the effectiveness of the sort key. If the Redshift customer has something to vacuum or analyze already in place, there's no harm in leaving that on. Redshift can recognize that there's no work to be done and skip the operation for that table. That said, if the customer is locking out users for a large period of time to run maintenance, that maintenance window should be revisited. I was at a very large bank recently, and they had been reserving much of the system on weekends for maintenance, and this is no longer needed because of these new features. How can I track the auto vacuum's historic work? For both the auto analyze and auto vacuum, the respective system tables, STL analyze and STL vacuum, record whether the operation was automatic or the initiating user. So it's easy to track through those two system tables. And then finally, how to know what's next for the Redshift management improvements. First off, the Redshift What's New page should be bookmarked in your browser, and we try to maintain that and keep that up to date. Your AWS account team can also give you updates and put you in touch with the Redshift team members for deeper dives and roadmap discussions. Your input is also really important for the direction of this work. Now let's talk about the Redshift Advisor. The Redshift Advisor was launched in mid-2018 and continues to learn new things to detect and suggest to Redshift cluster owners. Almost all the clusters have a recommendation to improve the cluster's performance. This is in excess of 96% of all the clusters across the fleet. This is another instance of the Redshift worker, and the advisor ties in nicely with the goal of automated sort key recommendations as well as automated distribution key recommendations. The Redshift Advisor can be found on the bottom left-hand side of the Redshift console. I'll show you a screenshot in a couple of slides. Okay, so here's a recap of today's session. The first thing we looked at was Elastic and Classic Resize, when to use them, and alert you to the new possibilities. You can scale your cluster up or down in just a couple of minutes. Next, we talked about concurrency scaling. Here's where you can choose which workload management queue you would like to generate a transient cluster, and potentially which workload management queue you'd want to not generate a transient cluster, and how this key feature will be free to almost all Redshift users. And then we talked about an update on the intelligent administration and maintenance. Here we looked at how automatic analyze and vacuum addresses that tedious activity, the ease of use of automated workload management, the sort and distribution keys potential for game-changing performance gains, plus the Redshift Advisor as a helpful asset for maintaining great performance on the cluster. So what's next? So for existing Redshift users, I think right away, this is a great time to go and look at the Redshift Advisor and see what the recommendations are for you. And then next, I think keeping an eye on your workload management with an eye towards how you can put concurrency scaling to work for you. And if you're new to Redshift, it starts with the Getting Started website on the URL on the screen there. We do have a Redshift free trial, and then your feedback is, of course, very welcome. This is Matt Skerritt. Thanks so much, and have a great day.